Luminosity. Luminosity is defined as the total power output of radiation emitted by a star. That. Now, so either you're gonna say the power output, or if you write it, then basically you can also say energy. Okay, let's write radiant energy per unit time. So that's basically the same thing, okay? In fact, I'll write it here. Radiant energy per unit time, like that. Now, the SI units, because it is power, so it's watts, and of course it is a scalar quantity. Now, usually with luminosity, the symbol we use is L, and there is a special symbol. Please note that luminosity of sun is written as this. Please. Okay, so if you see the symbol, you should know that they're talking about luminosity of sun, which is basically equal to 3.83 times 10 raised to power 26 watt. You don't need to remember this, by the way, it's fine. Now, any questions about luminosity, please let me know. Now, the next thing we should know is basically called the radiant flux. Some people call it radiant flux intensity, but that's fine. Radiant flux can be defined as amount of intensity observed normally means perpendicular through a surface per unit area of radiation measured on Earth. Now this is a bit of, you might think that it's a complex sort of definition, but I just want to, this is a keyword, I want to emphasize on that because writing perpendicular is very, very important. I'll just explain it in a bit, but before that, the symbol that we use for radiant flux is F. The SI units, because it is power basically being, transmitted 90 degrees to a surface per unit area, which means it is watts per meter square, right? Like that. please write this down, and then we're gonna go forward. So suppose, to explain it this way, I want to tell you that suppose this is the star, okay, and the star is shining, right? So what you see right now is basically the light that is being emitted by the star around everything, okay. So, and then of course some of this light is actually reaching the earth, wait a second please. So this is earth, and some of the light is basically reaching earth like this from the star, okay. Now so this is our earth, this is star, any star it could be, doesn't matter, and the distance from earth to the star is d, and we can say the luminosity of star is L, suppose, right? Oh, this looks very, very bad. Let me just make it in a different color so it's more. Okay, like that. So now, yeah, and this is basically this is the light emitted by star, right? Like that. Now the thing is that these quantities are related by each other by the formula that the radiant flux intensity F is equal to L over basically 4 pi d square, like that. Okay, so you need to remember this. D is the distance, as you can see, and L is the luminosity, F is the radiant flux intensity observed on Earth, okay. Now, to write it further, I would say that this is like, number one, the luminosity is the total radiation that leaves the star. Number two, the radiant flux intensity is the amount of radiation measured on Earth. Now, because star is twinkling every direction, so just all of the luminosity or all the energy does not reach us, so we can say by the time radiation reach us, it has spread out by a huge amount. Therefore, only a fraction of it is received on Earth. Alright, is that clear, Aman?
Yes, sir.
Oh my god. I started the meeting and I did not join the Zoom link. My god. That's not fair. Wait a second, please. Okay. Nadia and Suman and Gatika, everything is clear? Alright. Now, the relationship between the radiant flux intensity is of the inverse square law, which basically means that let's write inverse square law, which basically means that when you look at a certain star from a distance, suppose this is our star, so from the very source, if you basically look at one point, goes like this, and then it goes like this, goes like this, and goes like this. So what I'm saying is essentially, I'll make it like this, that if you go like this is the distance, so if you go a distance r, it means that it has actually been through this much of space. Do you guys understand this? Like this is the area that the light has reached, so it's a smaller area, so this distance I'm saying it's r, like that. So if you go through the same distance, which is another r, right? So then the area now, it seizes like 4 times of greater value. Do you guys understand this? And so on, right? So what I'm saying is that each time if f is here, if the radiant flux intensity f is at r distance, then it would be actually a quarter of f here, because radiant flux intensity f is inversely proportional to the distance squared. Do you guys understand this?
Sir, can you please repeat that?
Yes. If you look at it, because the rays are spreading, right? So as you go forward and forward, you might see that the area is getting bigger and bigger, right? What area are we really talking about? We're talking about the intensity, the radiant flux intensity of the star. Like star has this much, you know. Oh my god, let me move it here. Star has this much, suppose the initially the surface area, okay? This is the, suppose the surface area of the star. Wait a second. The surface area is 4 pi r square, right, of the star. And then as you go another r from the surface, like the radius equal to a radius of the star. So what happens is, like if you go to 2r, because of the function of square, basically the intensity reduces to a quarter. Do you understand?
Yes, sir.
So if you go 3r, the intensity would be 1 by 9 of it.
Okay.
Okay, now so what we're saying is that this equation F equals to L over 4 pi d square, this has certain assumptions as well. The first assumption that we're going to follow through is that the power of star radiates uniformly through space, which means that each side is getting equal power. Do you understand? And the other assumption of this equation is that no radiation is absorbed between star and Earth. So these are two assumptions that we got to make. You can actually make the third distance as well. You'll see it will be even larger. Just to clarify it even further, as you guys can see, the area that it falls is getting larger and larger. Understood?
So the second assumption means that all the radiation falls on Earth without getting spread out.
Like there's nothing in between that takes away that or absorbs it, right?
Okay.
Now, please note, here I note that number one, luminosity of a star is constant. Like it's a constant value because it's the power it's generating, right? So it's constant. The radiation flux follows, and this is very important, they will keep on asking this, follows an inverse square law. And the third thing is that, and that's the most important one, the greater the radiant flux intensity measured on Earth, the closer the star is to the Earth. And you will know this is one of the most important things in finding the distances of a particular star from Earth. Understood? Now, question please. So in a question, it says that the distance of a particular star is found to be 3.8 times 10 raised to power 18 meters. Okay. the radiant flux received is 2.6 times 10 raised to power minus 9 watt per meter square. Considering the star radiates uniformly through space, calculate its luminosity. Can you guys do it?
So is it 4.7 into 10 raised to 29?
Yes, 4.8 precisely.
So it's 7.1. Then it should be 7. Okay. So Gadika, all right. Are you sure is that the answer? Somebody did it wrong then. Oh my god. So you are L over 4 pi d square. So this is going to be 2.6 times 10 raised to minus 9. And 4 pi and 3.8 times 10 raised to power 18 whole square. And you're saying it is 7 times 10 raised to power 29 watts. Everybody got it? Yes.
Suman and Nadia and Aman. You guys are clear about it? Any questions about radiant flux intensity? All right. Now, so then let's go to the next thing, really. So now because the real thing is that the objective of our studying this is to study the objects found in space, right? So one of the ways of how we find stellar distances is through a method, and that's called basically standard candles. And we're gonna basically see what it means. Okay, first of all, what exactly is a standard candle? So in fact, let's write a question here. Let's do it like a question. What is a standard candle? Now, a standard candle is defined as an astronomical object which has a known luminosity due to a characteristic quality possessed, wrong spelling please, wait a second, possessed, it needs to have double S, okay, possessed by that class of object. We're going to learn about stellar classes too, so just hold your horses. All right, please write this definition, very very important. Now, so the examples of standard candles are number one, I write with a different color, okay, never mind. Cepheid variable stars. Now, so Cepheid variable star is basically a type of pulsating star that increases and decreases in brightness over a set time period. All right, now this variation has a well-defined relationship to the luminosity. Yes, please write this down. Now, I'll explain what standard candle is just in a bit. So just write this down. The next example that we look for is basically type 1A supernova, or let's write no way because there could be many. Okay, now type 1 supernova is basically a supernova explosion involving a white dwarf the luminosity at the time of explosion is always the same. That is why we want to, we want, basically standard candles are like, it's just like you bring in a candle that is of set size and set thread, so it gives you a certain brightness, and you already know that okay, this is the amount of brightness that this particular candle is going to give, and if you compare it with other candles you might see the differences. So basically we are setting certain standards that, okay, this is the indicator, and from this indicator we are going to build a relationship or build a reference to other stars that give light. Do you guys understand what I'm saying? Okay. Please write this down. Let me know if you have any questions.
So what is a white dwarf?
I'll tell you everything. You just gotta wait. Okay? Gatika, this is. Have you seen Pulp Fiction?
Have I seen what?
Movie Pulp
No.
Fiction. Hmm. You guys should watch Pulp Fiction, by the way. So, Pulp Fiction is a sort of movie that starts where it ends. Do you understand? So, the movie starting and ending is the same, and it goes through the time and tell you everything. Do you understand? So, what we're doing is right now we're learning, because it depends on so many factors, that we're learning one factor at each time, and then we're gonna combine everything that will make sense. Do you understand?
Yes, sir.
Right now, just focus on individual things that I'm telling you. Okay? By the way, white dwarf, for your information, is a star. Okay? Alright, it's type of star. In a much later stage of, a lifespan of star. But then, if I tell you, you'll get confused, so I don't want to, get into extra things right now. Alright, is that clear? Everybody, any questions now? Okay. Now, so what you guys need to understand is, now let's just write few things. So, measuring astronomical distances is an daunting or extremely difficult task. All right. So, a direct distance measurement is only possible if the object is close to the earth. So what you do? For distant objects, we use indirect methods like standard candles as a distance indicator. Okay, like that. Now, for example, we say, I'm just writing it in a different color, so later on you guys can, yeah, here. So if luminosity is known of a source, then the distance can be estimated based on how bright it appears on Earth. All right. For example, suppose It's just an example, the last example I'm giving, and then we're going to stop here and we're going to continue tomorrow. Suppose this is you and you're actually looking at a candle, literally a candle of this type from here. For the distance is known, suppose d. And now you put up similar candles at different distances. I'd say this is A, B, C, D. So you know their luminosity, how bright it looks, because the first one is the same. Now, would you be able to guess what is the distance of D? You know how you can guess? If you put candles okay. What I'm saying is, you guys, is that can you just guess, just a wild guess, that which candle is going to look the brightest first? Yes, please. Anyone? Suman, Aman, Gatika. Amongst all of these, which candle is going to be the brightest? Although they're providing the same amount of light, so the luminosity is same. Yes.
Sir D.
No, the one that is closest to you, Gatika. That's A. So, imagine if you see a car from a very far away, would its lights be brighter, or when it comes closer to you, it becomes brighter?
Closer.
So now if there are four same types of cars and they have the same light they're giving, so you could actually, if you know exactly what is the brightness of one car, then you can estimate that, okay, that car is this much, this far from it. Do you understand? So you're making A as your standard candle, and then you're comparing all of these with respect to A, that okay, if the A was the distance D from us, then what would B, D, and C would be. Do you understand? Like that. All right, now
Sir, will we get quantitative data from this?
yes, of course we are going to get quantitative data. Like for example, now we can say that basically astronomers measure the radiant flux intensity. That's what we're receiving from different stars, right? Of electromagnetic radiation arriving at the earth. Okay. Since luminosity is known as the object is a standard candle, that's what we wrote initially, right? The distance can be calculated using the inverse square law. What is that? F equals to L upon 4 by D square. That's how we're gonna get qualitative data, quantitative. Is that clear? Now?
Yes, sir.
Yes. So I'm gonna then basically continue this tomorrow, and yeah, so I don't know. Okay, if you have any questions, please let me know. So hopefully see you tomorrow then. Have a nice day. Bye.
Bye, sir.
Bye.